Okay, so thank you guys for tuning in to my talk. I'm excited to share with you some of the stuff that I've been working on over the last few months using phyllosilicates to hopefully decipher past aqueous conditions in Jezero crater on Mars. So as the title suggests, the minerals that I am working with are relevant to Jezero crater, which is the landing site for the Mars 2020 Perseverance rover. So it's thought that this crater used to be a closed basin with at least 2 inlets that produced features that look suspiciously like deltas. So as you can see with this figure here on the right from Gouge et al. 2017, we have iron and magnesium smectite clay minerals along with magnesium carbonates kind of modeling the surface of this heavily channeled delta that is overlying unaltered olivine-rich material. So based on the distribution of clay minerals on this delta and the fact that it is a delta, it's likely that these minerals are detrital rather than forming in situ. And so that gives us 2 opportunities for fluid rock interaction. So the first opportunity would be transportation. So they were likely formed somewhere up over here and then were transported to the delta surface where they were deposited, which gives us our second opportunity for fluid rock interaction. So those are the things we're keeping in mind as we're going through these experiments. So the main phase that I'm targeting is corinthite. This is a mixed layer clay comprised of 1-to-1 alternating layers of chlorite and smectite. On Earth, we commonly see this in hypersaline facies, hydrothermally altered basalts, and ultrabasic rocks, in burial diagenesis of volcanic rocks, and in contact metamorphism. There's a little bit of a controversy when it comes to mixed layer clays. Some folks suggest it is a transitional phase when altering from, for example, smectite to chlorite or vice versa, while others suggest it is in fact a distinct phase with its own thermodynamic properties. I actually think there's evidence for both, and so because of that, we're performing these experiments on the end members, smectite and chlorite, as well as the mineral corinthite itself. So the smectite mineral that we're using is nontronite. We are using synthetic and natural material. The natural material that we're using is NAU-1 Clay Mineral Society standard. For chlorite, we are using the natural phase rhapidolite and using the Clay Mineral Society standard CCA-2. So what I'm going to talk to you about today is just some preliminary results for some batch dissolution experiments that we've been doing. So these are basically to get an overall dissolution rate for these minerals so that when we perform these experiments a second time, we can do it with a little bit more accuracy and precision and have a little bit better material left over for microscopy work. So what I'm basically doing with these dissolution experiments is I'm taking 200 milliliters of 0.1 molar sodium chloride solution and titrating that with hydrogen chloride to the targeted pH, and then I'm reacting that with 0.1 grams of powdered mineral sample and leaving that to react in a shaker bath at 25 degrees C for a period of time. And over that period of time, we are occasionally extracting 10 milliliters of fluid and testing that fluid for a silica concentration on the atomic absorption spectrometer pictured here on the left. So the reason why we're looking at silica is because the release of silica from the phyllosilicate structure is deemed to be the rate limiting step when it comes to the dissolution of these minerals. So if we see this in solution, we know for a fact that this mineral is dissolving, and we can calculate a dissolution rate based on that information. So how do we calculate a dissolution rate? Well, I'm going to tell you, but first I just want to mention that the next few slides are going to have some equations on them. I'm not going to go into great detail on them, but I will kind of point out the relevant details that you need to know. So the first thing we need to do is correct for volume loss. Every time we're extracting 10 milliliters of fluid, we are changing the ratio of mineral to reacting fluid, and this is going to kind of mess up the concentration calculations a little bit. So we need to correct for that using this equation. Then we need to correct for the forward and backward reactions. So in a perfect world, we would see data that looks something like this, where we have nice data points. Every time we extract something, we'd have these nice data points as the mineral is dissolving. But of course, we don't live in a perfect world, and so we see something more like this. Of course, real data would actually be a lot more scattered than this, but for illustration purposes, I'm making it this nice pretty curve. So as this mineral is dissolving, also, a little bit of it is also precipitating, and that we need to correct for that. And for that, so the reaction is progressing forward and dissolving, and it's also going backwards and precipitating a little bit. And so to correct for that, the first thing we do is calculate the left side of this equation for every single data point, similarly to the way we did in the previous slide, except for the last 2 points. So what we do with those last 2 points is we actually consider those to be steady state. So when I say steady state, many of these experiments are not complete, and so it's actually just the average of the very last 2 points. So we use that and calculate every single timestamp and plot that on a graph similar to this, where we have concentration versus time. We then regress a trend line through that data and take the slope of that trend line and divide it by the surface area of the minerals, and that would be our apparent dissolution rate. So the surface areas that we're working with for non-ternite is 30.9 meters squared per gram, and for rhypidolite, 1.44 meters squared per gram, which is notably smaller. So as you can imagine, surface area affects dissolution rate quite significantly. If we have a larger surface area, it's going to be a lot slower than if we had a smaller surface area, and that'll make a lot more sense when we actually start looking at some real data. So once we do that, we can create a best fit model using this equation. Again, we have moles of steady state are just going to be the average of the last 2 points. And then we take the apparent dissolution rate as calculated in the previous slide and multiply that by the surface area or the slope of the trend line from the previous slide up here. And then we also use the intercept of that trend line in this equation. And once we do that, we can create a nice model that looks like these lines here. So these are some preliminary data for experiments conducted at pH 2. Here we have the y-axis is moles of silica, and the x-axis is time in seconds. So right off the bat, we'll notice that the synthetic non-ternite is releasing a lot more silica into solution and dissolving a lot more quickly than the natural non-ternite. This is to be expected. Synthetic minerals tend to be a lot more amorphous and a lot more pure, and so it's going to be easier to break those bonds, and it's going to have a lot less interference in dissolution without having contamination in the crystal structure. Another interesting thing is that rhypidolite, although it is putting significantly less silica in solution, it is still dissolving much more quickly than the other two minerals. And again, that's because of the surface area is a lot smaller. So if we had a surface area that was closer to the non-ternite, we would probably have a dissolution rate that it was much closer to the natural non-ternite rather than being faster than the synthetic non-ternite. So moving on to pH 3, very similar trends. We're still having the synthetic non-ternite releasing more silica in solution than the natural non-ternite and rhypidolite. Rhypidolite still has a faster dissolution rate than the synthetic non-ternite or the natural non-ternite. And again, these things are pretty expected. So we've looked at different phases of the same pH. So let's look at the same phase at different pHs. So this graph here on the right is the dissolution of synthetic non-ternite at pHs 2 in the diamonds, pH 3 in squares, pH 4 in the circles, and then pH 5 in the triangles. So the first thing you'll notice is that pH 4 is dissolving much slower. Sorry, not much slower. It's dissolving a little bit slower than pH 5, which is not to be expected. But because these numbers are so close together, that actually makes a little bit of sense. This is preliminary data, and so it's likely that when we perform these experiments the second time, we'll see those numbers change. And also, it's important to remember that the experiments for pH 4 are not complete, and so once those reactions progress a little bit more, we might see this number get a little bit closer to the pH 5. So finally, let's compare my very preliminary data with data reported by other researchers. So this graph here on the right is on the y-axis, we have the log of the rate in moles of mineral per meter squared per second, and then on the x-axis, we have pH. So the first thing you'll notice on here is that the non-ternite dissolution rates reported by Gainey et al. 2014 are slower than what we are reporting. The main reason for that is because Gainey et al. Was using a flow reactor, whereas we were using batch reactors. So flow reactors, as the name suggests, is going to simulate fluid flowing, so for example, a river, whereas batch reactors are going to simulate more stagnant water, similar to like sitting on a lake bed or something like that. Flow reactors tend to produce slower dissolution rates than the batch reactors. Another thing that's interesting to note is that the rhypidolite that we are reporting seems to be dissolving a little bit more slowly than the rhypidolite reported by Hammer et al. 2004. We are using very similar methods as far as the experiments are concerned. We are using I'm using his number for the surface area. And we're also using the exact same phase, the CCA-2. So one would think that these would be a little bit closer together. A couple of things to keep in mind. is that we only have 2 data points here. So if once we get pHs 4 and 5 for rapidolite, it might be more close. This trend line might be more close to the rapidolite that Hammer et al. Is reporting. And also, again, these are very preliminary data. So when we repeat these, we might see something a little bit closer to what Hammer is getting. So I hope I've convinced you that surface area is very important when it comes to dissolution rate. So again, we're seeing that these non-ternites are a lot bigger than the rapidolite, and so they are going to produce slower dissolution rates than the rapidolite. And so what does this have to do with Mars? Well, at this point, I can't really say a lot, but what I can say is that most likely more dissolution and alteration would have likely occurred on the delta surface after deposition rather than during transportation. And the reason why I say that is because in flow reactors, they produce slower dissolution rates than in batch reactors. And so one would think that that would translate to real world events. Oops, wrong way. Okay, so with that, I would like to thank Jacobs Technology as well as NASA for their funding and support. Of course, the department here at UNLV, and then the soil science team in the Hausrath lab here at UNLV. And with that, I will take any questions that you might have.
Thank you. We have time for 1 or 2 quick questions. Jay has a question.
Okay. So he says, do you have any idea why the pH dependence of your non-ternite dissolution is less than that of previous studies? You know, I don't. And at this point, because of the preliminary data, I imagine it might change once we're repeating these again. So yeah, honestly, I'm not 100% sure how to answer that question right now. Thank you for asking though.